Okay. Okay, great. So let's get started. Let's see if it really works. Yes. Okay. Yes. Let's get started with today's seminar. It is our pleasure to have here Miti Patel. She's a PhD student at the University of Leicester, working with Professor O'Brien on gamma ray burst. And I think that she's going to tell us about gamma ray burst today. So please.
Hi, everyone. So I'm a third-year PhD student, like Federico just introduced. So I will be talking about my work on GRB 2010-15A. It's interesting.
Few seconds should switch on.
Nice. Right, because I moved.
The first thing I'll be talking about is this GRB, which is a soft low luminosity GRB, and then I'm comparing it to a few others. And this paper, I've published this as a paper and it's out now, so anyone can check it out. So the introduction to gamma ray bursts is that they are short-lived transients which form from neutron star mergers or core collapse supernova, and they're the most energetic events in the universe, and they form a relativistic beamed jet, which we see either from the center or off axis, and the jet can have varying structure throughout, so more powerful in the center and gradually less powerful towards the outside. And we see an afterglow from this when it interacts with the surrounding material, and this can be seen across the entire electromagnetic spectrum, lasting days to months. And for the core collapse scenario, we see a supernova, and for the merger scenario, we see kilonova and gravitational waves. So the other thing is the emission that we see from these events is due to the synchrotron radiation, and there's also synchrotron self-competent, so which is inverse competent occurring in the same region as the synchrotron emission. So this can create very high energy photons that we detect in gamma rays and other parts of the spectrum. The emission is seen as a band function in the spectrum, and in the afterglow, we detect multiple power laws. So this example on the right is for the X-ray afterglow, which can have a prompt emission and then a steep decay, and sometimes a plateau or flaring activity, which is attributed to energy injection. And then we can also see a jet break, usually around 10 to the 4 to 10 to the 5 seconds. And this indicates the size of the opening angle of the jet. So all these factors can help us understand what's going on with the emission. And so now back to 2010-15A. This is what the prompt emission looks like. And you can see it's much heavier in the, brighter in the lower energy range from 15 to 25 kV. It's very obvious that there's a short spike. And when you look at all of the energy bands put together, you can see that there's a short spike and maybe some extended emission happening here. So this indicates the T90, these dashed black lines, which is 9.78 seconds from the swift bat detection. And in Fermi, there was a sub-threshold detection, and which lasted about 1 second. So it shows you that the detectors can have varying results based on which energy range they're looking at. So it doesn't really help us confidently determine whether it's a short or long GRB, because the dividing time is 2 seconds. So if one detector is giving us less than 2 and one is greater than 2, we need other methods of checking what kind of GRB this is. So we've looked at the isotropic energy and spectral peak energy to try and test it with the Amati relation. And then also the hardness and other methods. So the other thing that helps us understand it is the counterparts that I mentioned before, such as the supernova and kilonova. And we do see a supernova here. So we know that it's a long GRB. So just to explain this afterglow plot, this in the middle region here, we have the optical afterglow, and the blue region at the bottom is the X-ray afterglow. And then we have some radio observations over there. So the observational data was fit to a power law and then a supernova model for the light curve. And in the X-rays, we fit it to a broken power law, which indicates this plateau phase happening at very late times. Yeah, and then these solid lines here are the our best fit to the closure relations, which describe the synchrotron emission. And there's also a prediction for the end of the plateau here, which means that there should be a jet break after this time. So just to explain this plateau happening here could be explained by a few different scenarios. So there could be an off-axis viewing of the jet, but that would mean that there should be some brightening in the optical as well, which is hard to determine because we have a supernova happening as well. And the other thing could be the energy injection, which this line over here indicates, and a wind to ISM transition, which can also be described by the closure relations. So we've looked at both scenarios, and what we found was that energy injection shows a better fit to this data than the wind to ISM transition. So the energy injection coefficient here fits best to 0.24, which is similar to which is what we expect from a magnetar scenario. So I think the central engine could be a spinning magnetar. And for the spectral index, based on the spectral and temporal indices, we found that the electron spectral index should be 2.42, and that this is in the ISM slow cooling regime. So the Dynoti relation is what we use to predict this end of the plateau. That's based on the initial 1 second brightest peak from the GRB. So based on what happens in the first 1 second of the gamma ray burst in the gamma rays can predict what is going to happen in the X-rays at late times, which is a very interesting relation. And it shows that after this time, there should be a jet break, which our data doesn't disagree with that. So we've used that to estimate what the jet opening angle should be, which is greater than 16 degrees. And that is quite wide for a GRB, since the mean from what we know about GRB so far is 7 degrees. And this is the half jet opening angle, so measuring from the center of the jet to the outer side. So based from the supernova model that we fit, we've estimated the rise time, and this is compared to this paper by Tadia et al. And we have a rise time of about 13 days, and this is similar to the type 1C and 1CBL type supernova, which are related to GRBs. So we know that this is a typical rise time for this type of event. And based on that, we also checked the bolometric luminosity, which was minus 20.3 magnitudes, and that's brighter than a lot of other GRB supernovas. So that's an interesting result as well. But it could be to do with the initial low energy in the gamma rays relating to higher supernova energy. So based on the soft prompt emission, we've compared it to a few others which have a photon index of greater than 3, and we've seen that they lie in the low hardness ratio, and they also tend to have a lower T90 than the mean of long GRBs. So these 3 are long GRBs which are soft, and over here we have short GRBs which are soft, and they tend to have a T90 less than the average for their respective GRBs. And in the Amati relation plot, we find that these soft GRBs are also in the lower energy range in the spectral peak energy and the isotropic energy. And I've also looked into these other 2 GRBs, which are surprisingly far down on the plot. And 020903 was attributed to off-axis viewing, and 060218 is a shock breakout. So this is when the jet didn't successfully get released from the ejector. So there's a more circular burst rather than a jet. And these are the plots of the X-ray afterglows of these soft GRBs. We have the short GRB in purple, and the yellow is the general population of short GRBs, and the soft long GRBs in red, and the general all other long GRBs in gray. We can see that they lie below the median of where most X-ray afterglows are. So the softness of the gamma ray burst can determine how bright the X-ray afterglow luminosity is. This one that's an outlier is from the shock breakout. So we think that gives more energy in the X-rays than in the gamma rays. So as you can see here, it's very low in gamma rays, but higher than the other population in X-rays. Yeah, so that's what we found for these GRBs, and we think we will find a lot more of this kind of soft GRB from future missions, such as SWAM, Einstein probe, and Theseus in the future. So these have a lower spectral peak energy range, and the wide field of view instruments should be able to give us more information on what this sort of sample of GRBs looks like and enable more follow-up observations. And after this, I will talk about the GOTO telescope. So for the next part of this talk, I will be introducing this wide field rapid follow-up optical telescope designed to follow up gravitational waves and GRB triggers from Swift and Fermi. So the plan for this is a large field of view. So this is showing one of the nodes has a field of view of 40, and we have 2 of these domes in the north and 2 in the south. So there's one in La Palma and one in Australia. And in total, we have a 160 square degree coverage, and this can cover the entire sky in 3 days. And it has 4 different filters to view the night sky and the objects that we see. So it's great at detecting transients. Even while it's doing an all sky survey, it can find new objects. Yeah, so it's a modular scalable design, so we can grow this to have such a huge field of view. So the strategy is that they tile the sky, and when a trigger alert comes in, they decide which tiles need to be observed, and the there's a optimized scheduler which will be able to cover this within a single night. So on the day or on the night of the gravitational wave triggers, we should be able to get observations of the majority, well, 90% of their confidence region. And while there are no triggers, they will continue the all-sky survey. And all of this should happen at a very fast pace. It should be, we should get the reduced science images in 12 minutes. So this is the Marshall that we use to find transients without a trigger. So it will put all of the images from GOTO into this database where it will do difference imaging and it can find sources, and it gives a confidence rating based on machine learning models. So that's what we've used. And then after that, we have human vetting to decide if the source is a real transient or not. And we can alert the community about this. It also cross-matches with other catalogs to tell you about other galaxies in this region, or bright stars, or things within the solar system, so asteroids or anything else. And the other thing that we need help with to get this running is the templates. So to be able to get good science images, we need good templates. And currently, it's a lot of work to go through the entire night sky and sort through the templates to see what's good or bad. So we've set up a community science project where people can vet the images, vet the template images. And if you scan this QR code, it will take you to the GOTO Zooniverse webpage, where you can find a tutorial and you can choose whether this is a good or a bad template. So yeah, that's the end of my talk, and thank you for listening. Any questions?
Thank you so much. Any questions from the speaker?
All right. This GOTO. Telescope is already working, is already there, or is
yeah, it's already there. So we had the one of the domes in La Palma has been running and doing a testing phase for a couple of years, and now we've set up the second dome in La Palma and the 2 domes in Australia, and they're all starting to work now.
Okay.
Yeah.
So,
Any other questions?
Yeah, several curiosities.
Yes.
Yeah.
Go ahead.
Okay. What do you mean by checking the template is good?
Yeah, so we can
have a software that checks the position rules, stars are gate to see these things, or what?
yeah, so there can be some artifacts based on the detectors. So if there's like pileup or readout is not great, and sometimes the focusing or point spread function can be bad. So yeah, I think it's difficult to get software to check everything. So yeah, we rely on humans to do this.
Human eye.
Yeah. Yeah. And the tutorial should tell you what to look out for and stuff. Sometimes there can be partial cloud coverage in the sky or other things that affect the image.
Can I go ahead with that?
Sure.
Yeah.
So another thing, GOTO, if you have an interesting topic, like we found the kilonova. So I see that in a few seconds can go to the 20 magnitudes, okay?
Yeah.
But if there is something interesting, can you stop there on some target? Take a bit longer?
Yeah, so we can have deeper images that go to 23, 24 magnitudes. So yeah, I think with about 5 minutes of observations.
5 minutes?
No, I think more than, I think 5 minutes it would give you about 22 or something, which is on average what it uses for some of the images.
Can you remind us how big are the mirrors?
Oh, the mirrors, I think 40 centimeters, and there's 8 of those on each dome. So the coverage in the sky is 40 degrees for one dome, and then we have 4 of these, so 160 meters. Yes?
Is the archive accessible or in some way usable by other facilities that can check and counter check what you get, or is it just private from your project?
Oh, for the GOTO?
Yes, the archive.
The archive.
Yeah.
Yeah, so there is a tool which searches the database. It's called GOTO Archive Search. I can send you the link for that, or you can try find it online. I'm not sure, actually, I'm not sure if you need an account for that, a GOTO account, but yeah, so it's not really designed for follow-up of other objects. So once we find something from the GOTO telescope, we usually have other telescopes which can have deeper images search for follow-ups.
Okay, but the point is, if
Yeah,
it can be used for other components, would you prefer to keep it, let's say, privately or accessible only upon a direct request, or can it be made really publicly accessible after, I don't know, a week, a day, a year, I don't know.
Yeah, so I think if we do discover something from the observations, they get reported publicly. So, but I'm not sure
But that's
about.
another story.
Yeah, I'm not sure about the actual data.
Any other questions? Any questions from home?
Okay, go ahead.
Yeah, go ahead.
The comparison that you do in the Marshall are only with the catalog. It's not between images.
So it's between an older image from GOTO and a newer image. So
Okay, because it was written with catalogs. So
oh yeah, so we also check with caps logs. So this
okay, it's
image,
both.
yeah, it's doing both. So.
Do you know which software you're using for image difference images?
I'm not sure. I didn't write the software actually. Yeah.
So I have another question. You have a
Yeah.
Maybe a quick one regarding the earlier part of the talk with the magnetar. So can you put any realistic constraints on how long the magnetar injection was going on for you to observe this plateau feature, and any physical constraints that you can put at this remnant, just other than how long it was injecting energy?
We don't know, because we just see the plateau lasting until 10 to the 6 seconds, and I'm not sure if that's enough information to tell us how long the magnetar was injecting.
So you just arrive at the point where you get the accelerate the Q parameter.
Yeah, I just up to
and
the energy
you didn't check
coefficient.
the magnetic field period, the magnetar.
No.
So I have a question.
Yeah.
The main reason why to do, maybe if you know, to reject the ISM to wind transition, do you remember which was?
So I think it was that when we were fitting the expected temporal indices, it didn't match with the spectral index that we were seeing.
What was the relation?
Yeah, so it was just that we couldn't find any relation where they both were within the confidence region.
Okay, and if I can last thing. The energy. Okay, so you say something really curious to me. I something probably I also do. You got the end, the beginning of the. So where is the jet break? Probably by assuming the relation from the node. So you say that the break should not be before
This last point, yeah.
Yeah,
Yeah.
that's fine. And from that you got to the AI, compute the ISO and check the Amati relation, right?
The EISO is from the initial prompt gamma
Yeah,
ray.
you also need the measure of the angle that you get us in the position.
No, for EISO, it's assuming that it's spherically.
Sorry. Yes,
So
yes.
yeah, so without the correction for the.
So my question was, so you didn't check for the Girland relation or the collimated relation?
No, we haven't checked the.
No, this is very quite big. Okay.
Be consistent, I think.
Yeah, probably should.
Yeah, I think for
But
the.
it's usually quite
Yeah.
spread.
Any other questions?
Very quick. You know what will the GOTO telescope do when not observing every burst?
So it continues the all sky survey and some other surveys that are looking into specific parts of the sky. So there was a survey on large Magellanic clouds and looking in that area. So I think it has other priorities, but they are much lower priority than the GRB follow-up.
Okay, so it's not working like it said yet of searching for transients, monitoring, supernovae, this sort of things.
It's not monitoring, it continues to tile the entire sky. Yeah, so if it finds something, it will be in the catalog, but if it has something, it doesn't really schedule to look at something again.
Okay. Yes.
Thank you for the talk. Given that we know the redshift of these bursts and you provide the general figure, do you have any idea if the afterglow can be resolved at a certain point?
I don't know.
I'm asking because we had some late time radio observations.
Yeah.
PLBI, right?
Yeah.
So I was wondering, we don't see any expansion. At least we can resolve expansion for that.
Yeah.
I was asking.
Okay. So well, the redshift is 0.426.
Yeah.
It is lower than most other GRBs, but I'm not sure if it's very close enough.
Yeah.
Thank you. Yeah.
Thank you.
Yeah. No, okay. So if there are any other questions, let's thank Miti again. See you next week.
Any questions from
I don't think so. No, I asked, but no.
Okay.
Grazie per la.
No.